In this lecture, we are going to define the notion of a closed subset of a metric space. So I'm going to work through this definition and really everything in this lesson a bit faster than when we covered open sets, because if you look at this definition here, we're saying a set is closed if its complement, which I'm writing here with set difference notation, but you could also write B complement there, if the complement is open. So we define closed by saying the complement is open. Notice that doesn't mean that the set itself is not open. We're not saying a set B is closed if B is not open. So sets are not like doors and windows. They are not either open or closed here. So notice that closed and open are related, but they're not exactly saying that they are each other's antonyms. Okay, since our definition of a closed set depends heavily on our understanding of open sets, if you are not familiar with open sets, you need to stop watching and go back and revisit our lesson on open sets. So I gave a really thorough treatment of the basic notions underpinning open sets and metric spaces. I think it's worth taking a moment actually to pause and just restate this definition and make sure that you are ready to go. So give yourself a little test. What is an open set? What kind of properties do we expect open sets to have? And then I will come back and work through these 4 examples. I have 3 more examples, and then I have a proposition which is analogous to something that we've already covered for open sets. Okay, I'm going to work through these 4 examples now a little bit quickly because I'm depending on our prior knowledge of open sets. So for the first example, I've put the metric space M and the empty set together without specifying what the metric space here actually looks like. And that's because these 2 sets go hand in hand. So recall from our discussion of open sets that both M and the empty set are always open. So the metric space is an open set and the empty set is an open set, regardless of what the underlying metric is. So here's how you make this kind of argument. Since M complement is the empty set and the empty set is open, M is open. Oh, sorry, M is closed. Okay, so the complement of M is the empty set. That is an open set. Therefore, M is closed. Vice versa. So I'm not going to write it. I'll just say it out loud. Since the complement of the empty set is the metric space M, and the metric space M is open, the empty set is closed. So I said a moment ago that open and closed are not opposite notions in mathematics. And here we see that because in any metric space, M and the empty set are always both open and closed. So they have both of those properties. Okay, let's look at the second example. This is the interval from 0 to 1, including the endpoints. I'm trying to avoid saying the phrase closed interval, although it turns out it is closed. So as soon as I'm done with this, we can always call closed intervals closed, like you may have wanted to do so. Looking at the second example, what is the proper argument? The complement of this set is the union of 2 open intervals. So negative infinity up to 0, but not including it, union 1 to infinity. This is an open interval. This is an open interval. Any kind of union of open intervals is open. So since this is open, the original set is closed. So let me try to finish writing that out. So since this union of open intervals is open, the closed interval, which we can now correctly say, is closed. Okay, for this third one, I don't really want to go into the details. This is an R2. And what we have here, I just want to sketch kind of a picture. Get a tiny version of R2 right here. Okay. We are looking at all of the points whose distance to the origin is less than or equal to 10. So if this circle has radius 10, this is the set in question. Okay, so that's the set we are assessing. Let me give a visual illustration of why its complement is open. You could write down the details here. I'm just going to let you do that on your own. So imagine I take any point in the complement of the set A. Since it's in the complement, its distance to the origin is greater than 10, strictly greater than 10. So what you can do is design a radius that, say, if you want, you could give it some kind of prescriptive form, like it cuts you halfway back to 10. So what I'm trying to sketch here is imagine sort of defining an R so that I go kind of half of the distance to 10. I think you see what I'm doing. So I'm letting my neighborhood enclose this point and not touch the set A so that it's strictly in the complement. Okay. So since any point in the complement has a neighborhood around it that stays in the complement, I can design one like this. The complement is open, so this is closed. Okay. This is a closed interval. This third example is what you could call a closed disk. And then you could call closed ball the three-dimensional analog. So imagine a sphere in the interior, that's like a closed ball. But you could also use the word ball in a kind of general way. All right, I've done 3 examples. Let me pause if you'd like to think through the 3 that I've already done, and then go ahead and try the 4th one on your own. I'll come back and work through the details. All right, the 4th one is asking for us to assess rational numbers as a subset of the Euclidean real line. I omitted the notation, but hopefully it was implicitly clear that for number 2, I did intend for this interval to be situated on R. Okay. So here we're talking about rationals as they live on R. Q complement is literally Q complement. It's a set of irrational numbers. We talked about both rational and irrational numbers when we looked at open sets. Neither is open, so their complements are not closed. Let me just sketch a picture. Okay, imagine that C is an irrational number. You can try to take any open neighborhood of C, but by the density of rational numbers, any open neighborhood of C is going to scoop up a rational number. So no neighborhood can live in the set of irrational numbers. Therefore, C is not an interior point. So the set of irrational numbers is not open. Maybe I should write this out because of this kind of like you have to reverse your viewpoint while you're working through these. QC is not open. Therefore, Q, the set of rationals, is not closed. And essentially the exact same argument would tell you that irrationals is not closed. Okay, so to restate the conclusion of the 4th example, rationals are neither open nor closed, and irrationals are neither open nor closed. Okay, I'll give you another minute to finish writing this down, and then we will look at 3 more very similar examples before we do a couple short proofs. Okay, let's wrap up our examples with these 3 extra sets. We have here the set of integers as a subset of R. Then we have what I like to think of as the Archimedean set is a good name for this collection of numbers. So these are points of the form 1 over n, where n is a positive integer. And then lastly, any subset of a discrete metric space. Hopefully this final example is not a surprise. Let me do the first one, and then in the usual way, I'll pause and let you think about examples 2 and 3 before we tackle those together. I'll just go ahead and write out what the answer is here with a graphic illustration of why it's true. You could write this as a more formal union, but this is closed because what does the complement of the set of integers look like? Well, it's just going to be a picture of it. I don't know what I'm trying to sketch there, but imagine we just have some integers. The complement is a union of open intervals. It's an infinite union. You can kind of carefully phrase that with union notation if you'd like. But each of these little open intervals is an open interval. It's an open set. And then the complement is a union of open sets. Any kind of union of open sets is open. So since Z complement is open, Z complement is open, so Z is closed. Okay. Now think about this Archimedean set. This one is kind of tricky, and if you have your notes from open sets handy, you might want to look back at a discussion we had about this set, I think a few videos ago. If you start to sketch the Archimedean set, so draw the number line kind of like I did here, and you'll put on it the point 1, 1/2, a third, a fourth. It has something in common with Z in that it looks like discrete isolated points. There are actually definitions for both of those adjectives I just used, but I think the meaning is clear. So we've got kind of separated singleton points on the number line. So your first inclination might be to think that the Archimedean set is closed. However, it's not like Z, because as we get closer and closer to 0, those points kind of cluster up. 0 is the key place to look when you're trying to test a definition on something like the Archimedean set. So here, 0 is not in this set because it can't be presented this way. So notice 0 is in the complement. Let me just call this set A. However, no neighborhood of 0 lives in the complement. That's a very elaborate picture here. So here's 0. It's in the complement of the Archimedean set. But if I try to draw any kind of neighborhood around 0, I've got to go, well, to the left. That's fine. But I also have to go a little bit to the right. And the thing is, as soon as I travel any distance to the right from 0, there are going to be points of the form 1 over n in this set. Oh, that marker is really hard to see. So if the denominator here is large enough, I'll be able to find it in this set. That's called the Archimedean principle. It's not a precise statement of the Archimedean principle, but that's the idea here. That's why I call this the Archimedean set. So since no neighborhood of 0 is contained inside of the complement, 0 is not an interior point. Here I just want to bring up some earlier vocabulary. So 0 is not an interior point of the complement. Sorry, be really careful here. Switching back and forth between a set and its complement. So 0 is in the complement, but it's not an interior point of the complement. Therefore, the complement is not open. Okay, so since the complement is not open, the original set is not closed. So this third example is not closed. This is another set, if you compare it with our first look at it when we looked at open sets, it's neither open nor closed. It's also a great set to test topological conjectures on when you're working on R. So anytime you meet a new definition that's, say, to do with the structure of sets or topology or something like that, this set is a great thing to check. So I always recommend testing the entire space, the empty set, integers, rationals, your kind of famous name sets, but this is also a great one to have handy to look for perhaps a counterexample. Okay, so moving along, we have closed, not closed. For the third one, this one is actually very fast if you remember that every possible subset of a discrete metric space is open. So A, whatever A is, its complement is open. I don't need to know more than that. If I'm in a discrete metric space, every set is open. Therefore, since the complement must be open, the original set must be closed. Okay. So discrete metric space, every set is open and every set is closed. Okay, this is another great place to look for examples, counterexamples, kind of test your definitions whenever you meet them. So, have your sort of working sets that are perhaps subsets of just the Euclidean real number line. And then also keep in mind things like the discrete metric space. It's a really nice place to look for different types of behavior. We are going to wrap up this lesson now with a statement that very closely mirrors a statement that we saw about open sets. As we tested those 7 examples, the only information we had was the definition of a closed set. So I want to wrap up this lesson by bringing in this theorem, which just gives us a little bit more machinery to think about closed sets. And then in the next lesson, we will bring in a very useful characterization of closed sets, which you might want to look for when you want to assess whether or not a set is closed. This statement should look familiar because we had almost the exact same statement for open sets, but with some kind of switching here between the second and third bullet points. So the first one is that the entire metric space and the empty set are always closed. We've actually already established that, so we're not going to need to prove that one. And of course, that truth, again, comes from the fact that they are each other's complements and they are open. So since the complement of each of those is open, the original set is closed. For the second one, again with this kind of funny indexing here, what I'm saying is any kind of intersection of closed sets is closed. If you think back to this theorem, but for open sets, the statement was any kind of union of open sets is open. Here we're saying any kind of intersection of closed sets is closed. So again, very similar, but like key difference. And then the third one is a finite union of closed sets is closed. And of course, this partners up with a finite intersection of open sets is open. All right, statements 2 and 3 fall right out of the original statements about open sets together with De Morgan's laws, but I will go through the proof of each. And then just to kind of work on building up counterexamples from scratch, we will look at an infinite intersection of closed sets, which isn't closed. Before we move on, let me fix a mistake in something I just said. I paused the recording because I thought there's just a really high chance that I said the word closed when I meant open. That's not actually the mistake I made. I said that we would look at an infinite intersection that wasn't closed. I meant union. So we will finish by constructing a counterexample for the kind of infinite version of this third statement to emphasize that the finiteness is important. So we will have an infinite an infinite union. I'm about to do it again. An infinite union of closed sets, which is not itself closed. All right, to prove the second statement that any kind of intersection of closed sets is closed, I want to show that the complement of such an intersection is open. So let me write that down. Want to show that if I take this intersection, and I'll just write subscript lambda there, and assess the complement, I find that that's an open set. This is a complement of an intersection. So you could just go straight to De Morgan's laws. Oftentimes people prove De Morgan's laws with induction when there are more than one sets, and that doesn't actually apply here because this is a possibly uncountable intersection. However, De Morgan's law would still give it to you. I'm going to write just a proof kind of from scratch, just relying on the definition. So let me just take a point in the complement of this intersection. So this set, I'm going to take a point in this set and show that it is an interior point. So I'm going to form a neighborhood around it, which stays in this complement of the original intersection. Okay, so proof. Suppose I can find some point x, which is in the complement of the intersection. How do you land in that set? So what does it require to find yourself in the complement of this intersection? You are in the intersection if you're in every single member. So that's what it takes to be in an intersection. If x is in the complement, it means that there's at least one of these a sub lambda that does not contain x. I don't know how many such sets there are, but there's at least one. So thus, there exists some index, I'll just call it lambda naught subscript 0 from the indexing set so that x is not in that set. That puts x in the complement, which by hypothesis is open because this is closed. So since x is in the complement of this a sub lambda naught, and that's open, so the complement of our original member of this family is open. There exists an open neighborhood of x. I'll call it U. You could give it the form of an epsilon neighborhood if you like, but I'm just going to call it U. There's an open U containing x which stays inside of the set. So there exists an open set U so that x is in U which stays inside of this complement. Let me pause here and really just need 1 to 2 more sentences. See if you can get to the end. All right. I don't even think we need a full sentence. I think I'm just going to add something here. Since U is entirely contained in the complement of this set, A sub lambda naught, U, no part of U belongs to this intersection, okay, because it's not in at least one of these A sub lambda. So U is now a subset of the complement, this set here. Let's probably put a conclusion sentence on there. We've done it at this point. Let's just summarize. Okay, so I took a point from the complement. Therefore, it belongs to the complement of one of these sets, which is open. So I found an open set containing it, which stayed inside of the set. That entire open neighborhood now lands in the original complement, which means that around X, I can find a neighborhood which stays in this set. So this set is open. We weren't really trying to prove the complement is open. We're trying to prove the original intersection is closed. So since now we can say this, I'll just say, and so, and therefore, so it sounds kind of bad. The intersection is closed. All right, let's move on to the next statement, which is going to be kind of similar in theme. So if you'd like, you can pause and take a moment to try to prove that any finite union of closed sets is closed, and then I will work through the proof. I changed my mind for how I'm going to prove this. I'm just going to do a direct appeal to De Morgan's laws. Let me do that, and then I'll just mention why I didn't do this a moment ago. Okay. So De Morgan's law says that the complement of a union is the intersection of the complements, or the complement of an intersection is the union of the complements. Here we're going to take a complement of a union. So by De Morgan's laws, I want to take the complement of this union because we need to determine if the complement is open. Okay, so for De Morgan's laws, the complement of a union is the intersection of the complements, meaning the individual complements of each set. So here it's like the complement of an entire union. Here we are complementing each set and then taking their intersection. By hypothesis, A sub k is closed for each index k, which means A sub k complement is open. That just comes straight from the definition. And we've already proven that any kind of, sorry, here again, when you're discussing these theorems, it's easy to get mixed up with the language. Any finite intersection of open sets is open. That is something that we proved. So this is open. Okay. Let me state that though, so the reader doesn't have to do too much work. So since A sub k complement is open for each k, this finite intersection of open sets is also open. And here I will write by an earlier result that we saw, I think, in our second video on open sets. Now we know that this is open, but this is the complement of the set that we want to actually assess. So this set has to be closed. That's it. I didn't use De Morgan's laws when we looked at the earlier statement. because for some reason, when students learn De Morgan's laws, they don't always learn the kind of infinite version of it, which is what we would have needed a moment ago. This is just a finite union and the complement of a finite union. You can actually make this an infinite union. So it doesn't really matter how many sets you're taking the union of. The complement of the union will be the intersection of the complements regardless. However, for some reason, this version of De Morgan's laws is not always covered. So I didn't want to do that in case you haven't thought about extending De Morgan's laws in that manner to, all sorts of unions and intersections. And then also it's just nice to practice taking a point in the complement and showing that it's an interior point of the complement to determine that the complement is open and therefore the original set is closed. Okay, the chances that I misspoke and didn't catch myself at some point again, is high because all this kind of going back and forth between sets and their complements and open and close. Hopefully all of this is clear. Let's wrap up now with an example, in fact, probably several examples, demonstrating that you can take a union of closed sets, and if it's an infinite union, meaning I have infinitely many such closed sets, the union itself might not be closed. All right, as promised, let's go through a few examples that you can take an infinite union of closed sets and the resulting union is not closed. Once I do the first example, it's clear then how to construct like many more examples, but I'll give you, I think, 3 total, and that will be enough. Okay, first example. Let A sub n be the singleton 1 over n as a subset of R. Okay, so this is going to be an example on the real line. A singleton point is a closed set. Its complement looks like the union of 2 open intervals. So each A sub n is a closed singleton set. But if I take all of them, I get that Archimedean set that we determined a few minutes ago was not closed. I like this example because I always like to go back to this as a nice counterexample on the real number line. But now you see a prescriptive way to generate many more examples. Take any set of real numbers which you know is not closed, and then view it as the union of its singleton members. For example, how about just single rational numbers? Okay, I hope my notation is clear. I'm saying A sub r is R, where this is going to be a rational number. So if I take the union of all such, what I'm trying to build up here is just the set of rationals. Okay. So we could think of any not closed subset of R as an infinite union of its individual members, all of which are closed sets in their own right. So that's why it's so easy to create a counterexample to this statement. To give you an example on the number line, which looks a little bit different, let's work with that piece 1 over n as kind of like a fudge factor. So how about A sub n is 0 through 10 minus 1 over n. And there are different ways that you could modify this, obviously. So this is just one way to make a construction of closed sets using this kind of like a little bit of error term here. Each member of A sub n is going to look like a nice closed interval, but when I take the union, I'm going to have a not closed interval. So it's going to go from 0. This gets closer and closer and closer to 10 as the index n increases. So we're getting ever closer to 10, but none of these sets actually contains 10. So you should be able to work out that the union would look like this. Okay, I think I'll leave it there. You could try to make counterexamples in, say, R2, R3. You can look at maybe dis in the xy plane instead of closed intervals and see if you can kind of build up a union of dis, which gives you an open disk, perhaps, kind of like what I was doing here. Where should you not look for counterexamples? discrete metric space, right? Because every subset of a discrete metric space is both open and closed, so it's fruitless to try to look for counterexamples there. All right, I hope you enjoyed this first look at closed sets. We are going to continue talking about closed sets and related notions in the next lesson.